It's another thing which exists only in three dimensions. It's called scalar triple product. And it's basically to find to present or compute a scalar triple product. You need three vectors. Normally we call them A, B, and C in three dimensions. And the actual computation, it goes like this. You just dot product the first vector with the cross product of the last two. So this bracket, it returns a vector which you can dot product with another vector. So as a result, you will come up with a number. That's a number which is called scalar triple product. Computing that number, it goes like this. If I give the components to my vectors, and you see this time I do it in the abbreviated form. So here we have three components, A1, A2, A3. Here we have three components, B1, B2, B3. Here we get three components, C1, C2, C3. This short writing abbreviates all what I just said. Right? If I have these components, then first we can look how we compute the cross product of B and C. That will be the table like this, for which we perform all those steps I did twice today. Now, actually I did these steps here, so here's the expansion for when you put the cross over Y. Here's the expansion when you put your cross over J. Here's the expansion when you put the cross over K. Here. Now imagine now you have to do the second step in your computation of the scalar triple product. Then if you do the second step, you have to take this vector and you have to dot product it with the vector A. Vector A, it has these components, A1, A2, A3, that's here, it's from here. So when I take a dot product of this piece, this vector with this vector, I have to multiply first component here with the first component here, second component here with the second component here, last component here with the last component here. It will be a long writing. You don't have to copy that. It will be uploaded on the website. You will see this anyway, but just look at the, I'm going to replace this. So if I go for the scalar triple product, here what I will come up with. First component by first component here, second component by the second component here, last component, the third one, with the third component here. And that's the formula which delivers the scalar triple product. Now, again, on the efficiency side, on the efficiency memorizing this formula, you can write this again as a table of 3 times 3. Did I write this table anyway? Yes, I did. Here. You can write this in this form, and that's very easy to remember. This time, you write first row as the components of the vector A, second row as the components of the vector B, and last row as the components of the vector C. Forgive me this, I have to go quickly to the previous slide. Just was the slide this one, right? Just give me this 30 seconds break. What is this? I want to just copy this thing because I want to take it. I want to drag it. Just give me a second. I'll let you a chance to speak. I want to drag it across my scalar triple product. Here it is. Look at this. You just put it up like this. If you focus this on A1, the first term here, it's a product of this A1 by this table. And we know how to compute that table. It's a product across this diagonal. Take product across this diagonal. If you take this cross and you focus it on a second piece here, it will be product of this piece times this 2 times 2 table with the extra negative. And then when you focus this cross here, again, you end up with this little 2 times 2 table, which is sitting here, and you know how to compute that. So from the point of view of remembering how we compute the scalar triple product, that's the best way to remember it. You can't argue with that. That's the best way to remember it. And that's how we remember it. I mean, that's how we remember it. And I hope that's how you will remember it. Now, that's the computational side. Sorry, there was a question. Go ahead. Real quick. No, well, we have only 1 minute. Do you mind if you're just coming over? When I'm done, just come over and ask a question. I want to finish this. I want to just now, for the last 2 minutes, I want to just address what will be the geometrical meaning of the cross product. Triple scalar product. And the geometrical meaning of the triple scalar product, we can see that in the following fashion. Dot product, we all know what the dot product does in the geometrical sense. It multiplies the length of the vectors involved by the cos of the angle in between, right? Here's the angle in between. Here's the vector of the cross product, which is perpendicular, which is jointly perpendicular to my B and C. Here's a B, here's a C, here's A. It's a jointly perpendicular vector. The length of this vector, we discovered with you last time, that's the area of the underlying parallelogram in here. So from the geometrical point of view, this triple scalar product, it's the product of the length of the vector A, area of underlying parallelogram, and the cosine of the angle in between. What I'd like to focus your attention on is this length of A and the cos of the angle in between. What does it do geometrically? Geometrically, this is this right angle triangle, and the cosine is the adjacent angle to one of the sides of my right angle triangle. So when you multiply the length of this vector by the cosine in here, you will end up with the length of this piece. So all you're looking here at is the area of the underlying parallelogram times the length or the height of the parallelepiped based on these three vectors. And from the elementary geometry, we know that the product of the area of the parallelogram times the height of the parallelepiped delivers the volume of that parallelepiped. So the scalar triple product geometrically, it delivers the volume of that parallelepiped. With one extra correction, it delivers the signed volume. It might be plus or might be minus, depending on the sign of this cos. So in fact, the triple scalar product, it will deliver either plus or minus of the volume of that parallelogram. The absolute value of V, that's what I said in here, the absolute value of V is the volume, sorry, I said volume of the parallelogram, certainly I misspoke, I mean the volume of the parallelepiped, based on those three vectors. And that's where I will stop. Thank you very much. You're free to go.